Now here are some examples where we're demonstrating again that a repeating decimal can be written as a fraction, but we have to be more careful with these examples because more than one digit, more than one number will be repeating. So let's use and demonstrate the repeating decimal of 0.83333. So 0.83333. So we want to show and demonstrate that that can be written as a ratio of an integer and a natural number, a over b. But it's important to note here, again, that the 8 is not repeating in this example. It's 0.8333333. It's not 83838383 or 0.88888. It's only the 3 that's repeating. It's not the 8. The 8 is not repeating. So when we go to do this algebraically, when we set up our equation and define our variable, we have to make sure that we define that x is going to be equal to 0.83 repeating. And when we expand that, the 3 is the only digit that's repeating. The 8 is not. So now, let's notice what happens when we multiply that one-digit repeating decimal by 10. And let's choose 10 because only one digit is repeating, so that means that would be 10 to the first. So that would give us 10x equals 8.33333. So the decimal point slides one space to the right, and the new number looks very similar to the original number, right? We had 0.83333, now we have 8.33333. So we have still that same 0.33333. So if we subtract, as shown, if we subtract x on both sides, as shown here, we're doing 10x minus x will give us 9x. And here we can do 8.3 repeating minus 0.83 repeating, and we can do that. That's still a balanced equation because remember, x equals 0.8333333. So we are subtracting the same thing from both sides, and that gives us 9x equals 7.5. This process is a clever way to make the repeating decimal disappear. We don't have the 0.33333's anymore. So we end up with 9x equals 7.5. So now to solve for x, we'll multiply both sides of the equation by 10, which gives us 90x equals 75. Dividing both sides by 90 gives us that x equals 75 over 90, which simplifies and reduces to x equals 5/6. So our repeating decimal of 0.83333, or 0.83 repeating, as a fraction is 5/6. We were able to convert from that decimal form to the fraction form. We just had to be careful because we had a digit that wasn't repeating, which was different from our other examples where it was all the repeating part was like the only digit in the decimal. Let's take a look at another example. So here we we're not going to look at a different example. Let's keep with this same example because there are more than one option to solve or to convert this decimal to a fraction, right? We're still working with 0.8333 repeating, and it's still good to note that the 8 is not repeating. We're still going to define x as that repeating decimal, but now we don't necessarily have to multiply by 10. We could multiply by 100. You can think that there's 2 digits in the number, so you can multiply by 100. Well, there's more than 2 digits in the number because the 3 is repeating, but you visually see only an 8 and a 3, 2 different digits only. So if we multiply both sides of the equation by 100, we end up with 100x equals 83.333.3 repeating. And the decimal point is sliding 2 digits to the right, and the new number looks similar to the original number. So now we have 100x equals 83.33333 repeating. If we now multiply x by 10, because now we have to multiply that variable by 10 to show, again, we're trying to show a way to get rid of the repeating decimals, and if we multiply just by x, we're going to end up with still some repeating decimals. So we have to multiply x by 10, and then if we subtract, as shown, if we subtract now 10x from both sides of the equal sign, we'll end up with 90x equals 75. Dividing both sides by 90, we get x equals 75 over 90, which is 5 over 6, which is exactly what we got in the last time. So this is just showing you have two options where you could multiply by 10 or by 100. You just have to then be careful later on. You would have to multiply. If you multiply by more digits or by 10 to something higher than how many repeating digits there are, you're going to have to multiply by that same number later on just to balance out the equation. Again, our whole purpose is to remove the repeating part of the decimal. So when working with our equation, we just have to make sure we do that and be on the lookout for that as we solve. Now here's a different example where we actually have to multiply by 100. Here we're demonstrating that we have the repeating decimal of 0.9166666. So now we want to show that that can be written as the ratio of an integer and a natural number. But it's important to note that now two digits are not repeating. The 9 and the 1 are both not repeating. It's only the 6. So we're going to define x as 0.916 repeating, or 0.9166666. And again, because there are two digits not repeating, the 9 and the 1, we have to multiply both sides by 100. That will give us 100x equals 91.66666. The decimal point slides 2 places to the right, and the new number looks similar to the original number, but it's almost like we're taking the two digits that are not repeating and we're moving them before the decimal or to the left of the decimal. So that's a good way to remember and think of what you should multiply, what power of 10 you should use to multiply both sides of the equation by, because that will help you, again, remove and make the repeating part of the decimal disappear. Now, we still have it, so in order to get rid of it now, we have to actually subtract x from both sides. And that will give us 99x equals 90.75. See, the repeating part of the decimal number has disappeared. And now we can multiply both sides of the equation by 100. That will get rid of the decimal part of the equation, which gives us 9,900. X equals 9,075. Dividing both sides by 9,900 gives us that x equals 9,075 over 9,900, but that does reduce then to 11 over 12. So that repeating decimal could be written as a ratio, but we just had to be careful because two of the digits were not repeating. So in your examples or in problems when you're converting from decimals to fractions and you have these repeating decimals, you just have to note, are all the digits repeating, or are there some that don't? And then just take that into consideration when you're using your algebraic equation to do your process.